All right, hello, welcome to the next week. And so we are now going to start a new data structure called trees, and it's very serendipitous that the color that I chose for this was green. I followed them in order, so this was by chance, and it was beautiful. See, they go in this order. Okay, so let's get started. The tree data structure. If you pause and read this comic, that is hilarious. This top thing is known as a tree data structure, and we will be drawing many of these today, next week, all the time from now on. So if you hated linked lists, you are not in for a treat at all for the next couple weeks, because we're going to have extra pointers now, and I'm very sorry about that, but it's just the way life goes sometimes. So let's talk about binary trees. What in the world? First of all, what in the world is just a tree? So a tree, it's a new kind of data structure, and it consists of things called nodes still. So we still call them nodes. So like here is a tree. It's not a binary tree yet, and we'll talk about what that means. But what it's doing is it's holding information. It's got some keys. There's a node with a 2 key, a node with a 7 key, a node with a 5 key, things like that. And every node in a tree has a list of pointers. It could be multiple. Okay, so it's a list this time. It's not just one, like a linked list. Maybe that's a linked list right there, but no, this whole thing is a tree. You can have multiple nodes pointed to by a single node. So this one has 2 that it's pointing to, and this one has 3 that it's pointing to. Okay? No pointer, though, is allowed to be duplicated, so we can't have this. That is no longer a tree. And there's a special root node that nobody else points to. So again, can't have something like that. It's no longer a tree. This is called the root of the tree. It's where everything begins. Okay? In this class, we care about binary trees, and that means that we only ever have 2 pointers coming out of each node. Maybe I should rearrange these words to say that. And it's not just 2, at most 2. So it's still fine to have things like boop, boop, boop. That's still a tree, but the idea is you can only ever have 2 things coming out of a node. Okay? So this is totally fine. 1's fine. Obviously at the very bottom, 0 is fine. You can only have 1 or 2 or 0 things coming out of a single node and call it a binary tree. Okay, so we got binary, by, of course, 2 pointers coming out of each node. All right, so let me draw for you now some sample binary trees. And I mean, the one that I'm going to keep drawing forever is a one that holds a bunch of ints. So let me draw a nice binary tree for you that holds some ints. It's got, like, I don't know, 1, then 3, and 5, and I don't know, 7, -42. This is a binary tree that holds ints. Okay, it only has at most 2 pointers coming out of each node, and this right here is the root. Okay. Another thing that you might be familiar with is like a flowchart form of a program. Like, hey, if x is true, then go and run this code. I don't know, launch missile. If it's false, I don't know, maybe your program either launches a missile or makes you coffee. Something like that. And that's a valid binary tree. Obviously, you can check for more things after this, but like programming language, if statements can be represented by a binary tree if you want. And then also, inside of your compiler, when you say G++, please compile my code, it's forming what are known as syntax trees for the language itself that it's trying to compile for you. So it knows about C++, it knows what C++ is supposed to look like, and if it ever gets to a place where it has a malformed syntax tree, it gives you a compile time error. So for example, here's like a syntax tree for a while loop, let's say. We'll make a node for your compiler will transform this while loop, for example, into the following syntax tree. It's got while, and you got your condition, And then you have all the statements of the body. So you got like statement 1, then you got statement 2, and you can have multiple. And then that's it. So this is how inside of your compiler it might represent this while node. It's like, all right, I'm going to make a tree with the root called while. The condition is going to be right here. Maybe it was like, I don't know, 2 plus 2. So it would hold like a plus and then a 2 and then a 2. That was the condition. And then it would hold the body. The body would go right here, and it's just a bunch of statements. So maybe it would do like, I don't know, statement 1, and then followed by statement 2, and that would be a tree. Okay? So it's rooted with while. That's how you know, hey, this is a while loop that I just translated into tree form so I can then go and compile it. So this is all very useful stuff, and you'll be seeing this for the rest of your computer science career, so I'm excited to teach it to you. Okay, so how in the world are we going to represent these trees inside of code? Like, we know what nodes are, but how do we define those structs? Okay, and so I lied a little bit when I said that the list of pointers to his children is the only thing, because we're also going to save a pointer to the parent. And these are interesting terminology, as you can tell. Like here's a node. It has children, and it is the parent of these children. I don't know, A, B, C. So A is the root, and the parent of B and C, we say. And B and C are the children of A. A bunch of like lifelike metaphors going on with trees. Okay, so that's the idea there. So inside of every node, we're also secretly going to store the parent. Okay? Boop. We'll store the parent node as well. So that's a cheating thing maybe in your mind, but this is what we're going to store. These are parent pointers now. And so here's how it's going to look. We're going to say something like struct tree node, and the things that we need to store inside are the value of the key, so whatever data we're storing. Maybe it's like an int, or in my case it's a bunch of characters, right? So char data perhaps, and then we need to store pointers to the two nodes that could potentially be our children. It's possible to have like one child here. This is okay, just a single child here. But then at the end of the day, how do you know when you're done? Like, how do you know that B has no child over here to the right? Well, that's going to be represented with, you guessed it, null pointers. So a bunch of null pointers all around to say when to stop. Okay, these are all null. So they mark the end of a little subtree. How do I want to say this? They mark the end, let's say. All right, so we're going to store data, and we also need to store the pointers that a node could potentially have. So I could have two, and we call them left and right. So tree node star left, that's your left child, potentially, if you're not null. And then we're going to do the same thing for right. Okay? Okay. And then also I'm going to save the parent. That will be helpful for some algorithms we'll talk about, if not this class, or if not this week, next week. Okay, so you got your left. So let's talk about it from A's perspective, the A node's perspective. It's got a left pointer to B, the B node, a right pointer to the C node. It has no parent pointer. The root has a null parent pointer. Okay, Maybe I should draw that in green, as I was doing. Whee. Everybody else has a parent pointer, though. And then once you get to the very bottom, you have null. Okay? So, this is a tree node struct that we can use to build a big, long tree. Okay? And I guess the reason they call it a tree is that it's like upside down. Like if you were to rotate this, now it looks like the branches of a tree, right? Or alternatively, you can pretend that the tree is up here. Oops. You can pretend that the tree is up here, maybe. I don't know how I want to draw this. And these are like its roots, deep underground, perhaps. Okay. All right, so let's now make some simple trees in code. So let's make this tree right here. Let's do 42 at the top. That can be the root. Why not? Then 3, 4, and then maybe 7 can be the left child of the 4, and then these are all going to be finished. So the idea is these mark the end. Like there is no left and right for 3, there's no left and right for 7, there's no right for 4. So we're going to represent those with null. Okay, so I'll draw little x's to mean null here. Boop, boop. Null, null. So let me make this inside of code. Okay, so 42 is the root. And its children are 3 and 4. Oops. And when I say 42, it's the 42 node. It's the node with 42 as its key. Children are the 3 and 4 nodes. And then 4's left child is the 7 node. Oops. Okay. And then everybody who doesn't have a left or a right child that pointer is set to null. Also, the root's parent pointer is set to null. Okay, so let's go to code now. Let me see if I can copy this. That would be super helpful. Let's make this happen. Looks like it's lecture 17, so welcome. Okay. What do I want to call this? I don't know. Simple tree. And I think we only need one. Alright, so here's my tree node struct. And so now if I want to make a tree, I have to start some things off. I don't have to make these nodes on the heap, but usually you do, just like for linked lists. So tree node 42 equals new tree node. Okay. And I forgot my little pointer symbol, of course. So I'm going to do this for every single node that we have. I need 42, a 3, and a 4, and a 7. Okay. Okay. So now let's set up the pointers properly. So, or first, how about the data actually? So 42, its data is going to be 42. So this is going to be 3, that'll be 4, this will be 7. Okay, so now let's set up the left and right pointers. So it looks like 42's left child is going to be 3, right? It'll hold a pointer to the 3 node. And then its right child is going to be 4, the 4 node. Because here is the left, here's the right. So 42's left child is 3, 42's right child is 4. The node itself, that is. And then let's talk about 3. What's 3's left child? Well, it has no children at all. So it's going to hold a null pointer for both. Okay, that's how you know it's done. There's no more little subtree inside of it. And then 4's left is 7, and 4's right is null. Okay, and that just leaves us with 7 now. The 7 node has also no children, so its left and right will both be null. Ah, I always mess that up. So 7, there we go. And now I have a working tree, and I've built up the proper things. The one thing that I do want to add, though, is the parent pointers, because they will make certain algorithms easier. Okay, so 42 has no parent. It's like nothing there. So but everybody else has a parent. 3's parent and 4's parent are both 42. So 3's parent is equal to 4's parent, which is equal to 42, the 42 node. And then 7's parent is 4. Okay, so now we have a final working tree, and this program does nothing, but we can make sure that it actually works, I guess. Alright, at least it compiled. That's an effort in itself. And it does absolutely nothing. Well, we can examine this tree. We'll be like, all right, the root of this tree (42). We can be like, all right, what is the root's data? What's the root's left's data? What's the root's right's data? Ah. So this should be 42. If we go to the left and get the data, this should be 3. If we go to the right and get the data, the right of 42, then we'll get 4. Okay. Boop. Boop. And did I not set the data properly? Oh, sorry. I used char, but now I'm using ints. Sorry if you've been yelling at me through the screen. Looks like most of those were unprintable, but apparently 42 is the star character. That's fun. So 42, 3, and 4. Cool. So this tree is working. It's just a new way of arranging data, and we'll see soon what it's good for. So let's talk about some terminology now. There's a lot. Sorry about this. You'll read it in your book, of course. But let me just give you a sneak peek at all of this. This is, again, not a binary tree, but it's a tree. So we can talk about things. You got your root, and every connection in between nodes, left and right for us, this is going to be called an edge. Every little connection, okay? That's the link between a node and its child. We're going to call that an edge, okay? And that will become necessary to talk about for future definitions down here. Then we have leaves, which is fun, just with the tree terminology. A leaf is a node with no children. So down here at the bottom here, H and I were leaf nodes. 3 was a leaf node. 7 was a leaf node. 4 is not a leaf node here because it has one child. Okay, so it's an internal node. An internal node is a node with at least one child. Okay, so this is a leaf, but this one is an internal node because it has a subtree here. Okay. The parent is the immediate ancestor. We've talked about this. So Q's parent is P. G's parent is L. Maybe its grandparent. One of its grandparents is A. Sometimes you might have multiple. let's see here. Or actually, no, that could have been a lie. Only one grandparent, it looks like, usually. You just go up to the parent. The parent of your parent is your grandparent. There's only one. Okay. You can have uncles, though. Roots are the thing up at the top. So it looks like this is a little too far ahead. There we go. So it's like the granddaddy of the tree. There is, like, time began and there was P, okay? It had all these children who then had their children, things like that. It's like a family tree, I guess. So that's the root. The root's up at the top. It has children but no parent. And all right, now let's talk about things that require this idea of edges. So the depth of a node is the number of edges on a path to it from the root. And there's only ever going to be one path. There's only ever one way to get to a node. Oops. There we go. No. Well, let's do it again then. There we go. There's only ever one way to get to a node. You have to follow certain left and right pointers, things like that. So the depth of a node is going to be the number of edges that you need to take on a path from the root to get to that node. So P's depth is 0. Q's depth is 1, because you only have to follow one edge to get to it. And then B's depth is 2, because you have to follow 2 edges to get to it. Okay, so that's what depth means. And then you can put all the nodes with a certain depth together with this idea of levels. So you can say, all right, what are all the things at level 0? Well, that's just P. What are all the things at level 1? What are all the nodes with depth 1? For this particular tree, it's Q and R. What are all the nodes with depth 2? What are all the nodes at level 2? Okay, hopefully that makes sense. And then the height of a tree is the largest depth you could possibly have for any node. So maybe like this happened like here. This would be a node with the largest possible depth. Okay, and that is the height of a tree. So the height of the tree is, look at all the nodes, look at all the leaves, I guess. Figure out what the depth of those are, and then the one that's the farthest down marks the height of the tree. That's how far the tree goes down into the ground, I guess. So there's 1, 2, 3, 4 edges to these smallest children. 1, 2, 3, 4 on each side. So these are all at the same level. They all have the same depth. And so the height of the tree is 1, 2, 3, 4, because that's the most number of edges you'd have to traverse to get to a node. Okay? So in this tree, the height is 4. Okay, so with all that terminology now, I'll just keep coming back to it, so it will essentially get ingrained in your mind. Let's talk about some other kinds of trees. So we can talk about trees themselves now. And so there are a few definitions. Full, complete, perfect, and balanced are the ones that I want you to understand. Honestly, the ones that are going to be most useful to us in this class are probably complete. That will help when we talk about heaps. We'll need a complete tree. And then perfect is like the one that you have in your mind when you're thinking about the running time. That will be helpful. And then also balanced is going to come into play here. I don't usually talk about full all that much. So a full tree is every node either has 0 or 2 children. So here's a tree that's full. Boop. So this node, 2 children. This node, 2 children. This node, 0 children. That's allowed. That's a full tree. A complete tree, this one's also complete, but the idea of a complete tree is that every level has every possible node. So they all got 2 children up until the last level of the tree, at which point the nodes are filled in from left to right, if that makes sense. So you start over here, like if you needed to add nodes to this tree now, you'd have to start over here if you wanted to keep the tree complete. Okay? You gotta go from left to right on the last level. Okay, so this one's complete. It's full. This one's actually also complete. This one's complete. And then a perfect tree is like the one you have in your mind. Like, oh man, everybody's got two children, and all the leaf nodes are at the same level. Beautiful. All the internal nodes have 2 children. That is lovely. These are what perfect trees look like. This is a perfect tree. This is a perfect tree. I think it makes sense in your mind now. These are all perfect trees. Okay. How many nodes, maybe pause and take a second to think about this. How many nodes must perfect binary trees have? So this one has 1. This one has 3. This one has, have you found the pattern? 7. So it's always 2 to the n to some n minus 1. Okay, this one's 2 to the 1 minus 1. This one's 2 to the 3 minus 1. And then a balanced tree is just one that isn't leaning to one side or another. These are all really balanced trees that I've drawn. A tree that is very imbalanced would look something like this. Boop. Oh, and then maybe down here it has 2 children. Okay, this one's very not balanced. Okay, so hopefully all these make sense. This is nice if you're a visual learner because trees are just a bunch of pictures that we can draw for ourselves. They have a lot more structure than a list. And okay, lists are trees are cool, sure. What's the point of any of this? Well, the point is that we want to organize data in a way that allows us to search very, very fast. Okay, so we can pick the order that we want, and we can put things into a tree, and by following left and right pointers, we can get to places very quickly. Okay, so if the tree is balanced, every time you pick, hey, I gotta go left, hey, I gotta go right, you split the search space in half every time. Okay, so maybe now it might make sense why we why there's a binary in here, kind of close to binary search almost. So you split the search space in half every time you go left or right. Like you only have these nodes to consider now. If you went over here, you only have these nodes to consider. Half the tree goes away. That's kind of cool. And because of that, because half the tree goes away, we end up with logarithmic time searches for balanced trees. And an example of a balanced tree that you might be familiar with is Morse code, if you've heard of that. It is essentially a balanced binary tree where you have some dots or dashes, and each time you have dots, those can be followed by either more dots or some dashes, things like that. And then every time you do enough of these, you end up with a character or some kind of symbol. Okay, so that is a little bit of motivation, and hopefully that helps, because this is kind of theoretical, I guess. So what I do want to talk about now is, okay, if we want to search, we need to put things in some kind of order. So yeah, I should say that. Oh, hello. If we want to search fast, we need some kind of order. What order will that be? Cool. Well, it can be whatever you want as long as you're consistent, but what we're going to talk about, a way to bring order to a tree, is something called a binary search tree. Which I will lovingly refer to as a BST because we're going to say this word a lot. So how in the world can we take advantage of order is the question. And so in comes BSTs, or binary search trees. And every binary search tree has a property that it respects. Okay, so if you have a binary search tree, it respects this binary search tree property. So for every node in your tree, its key, the key at that node, is greater than every node in its left subtree and less than every node in its right subtree. And so maybe we should talk about subtrees very quickly. Let's give myself some space. So no bold, please. Every time you go left or right, you end up, the node there is technically the root of a new tree. So I'm going to draw this particular tree for a reason. 5, 3, 1, 4, 10, and I don't know, 42. And the idea is, if you look here, and you go, like, say you go left, and now you're sitting at the 3 node. Well, you can pretend, just like we did for lists, you can pretend that that is the start of another tree. Not a list anymore, but a tree. So here's its root, here's its children. Just from that point, from 3's point of view, it could just be a tree by itself. You see that? That's a subtree. And so you can have many subtrees. Any node starts a subtree. Like here's a little subtree for 10. Here's 42 subtree. It's only got one node. Okay? You can have an empty subtree because these are all null. The empty list could represent that. Okay? Should probably close that so I don't get any more notifications. But okay, now let's talk about the binary search tree property. So for every node, its key, so the thing inside of it, that's determining where it is in the tree, it's greater than every node in its left subtree, and it's less than every node in its right subtree. Okay, so there's no, usually there's no duplicates in a binary search tree. Your book says otherwise, but usually there are no duplicates. In a BST. So here is why this is useful. Let me show you this. Let's use rainbow because it's a pretty property. So here's the 5 node, it's the root. And if this is a binary search tree like I'm claiming it is, for each node, from each node's point of view, if we go inside of the left subtree and look at every single node, they're all going to be smaller than the 5. Do you see that? 3 smaller than 5, 1 smaller than 5, 4 smaller than 5. Every node in the entire subtree needs to have that property. It needs to be, this node better be greater than everything here. And it also better be less than everything here. Okay, so yes, 10 is smaller than 5. Yes, 42 is smaller than 5. So that's correct from 5's point of view. Now we have to do it for every other node in the tree. Okay, so is there a 3? So look at 3. Is everything over here smaller? And is everything over here greater? Yes, it's a binary search tree. Rooted at 3 for now. Okay, let's try 10. Is everything over here smaller? Well, there's nothing there, sure. Is everything over here greater? Yes, it's fine there. And then all these leaf nodes, well, there's nothing to the left and the right, so trivially, they respect this property. Okay, so that is what it means to be a binary search tree, and I think you might understand the beauty of it now. Let's say I wanted to search for the key 4. Starting at 5, I know, just based on the fact that this is a BST, I know that if 4 was in this tree, I better look over here. Okay, it's got to be somewhere over here. And then you suddenly see 3, and you're like, oh, well, if I'm looking for 4, I better go right. You see that? And now suddenly you find it. Or if you were looking for like 4.5, you'd like try to go this way, and you'd end up nowhere. And so it wasn't in the tree. Okay, so hopefully that makes sense. Let's talk about that in much more detail. So how in the world shall we search a BST? Well, we're essentially using binary search. So let me copy my favorite tree that I drew for you over to here. And I don't think we need the subtree anymore. We understand subtrees. So in order to search a binary search tree, the process is, well, you start at the root always. And you go left or right depending on what you're looking for. Because you know it's a BST, you have a very strong notion of where things are or could be in this tree. So if the root doesn't have the value you're looking for, I think I should put this up here in parentheses, perhaps. There. Okay, so if you go left, that meant that you were looking for something smaller than the root. And if you go right, then you're looking for something larger. And because you're at a new subtree, you can pretend that it's the root now, and you do this whole process over again. Until you either find the node you're looking for, or hit null, in which case you didn't find it. So let's have two examples all over again. So let's first search for I don't know, let's search for 42. And then let's search for 7. Okay, so if we search for 42, we start at the root, and because we see that we have a 5 here, we know that 42 is bigger, and if that, because this is a binary search tree, that means it better be in this subtree over here, so we better go right. Okay, so we're going to go right, and now we're sitting at this 10 node, and we do this whole process. It's the root of a new subtree, so we'll look and see, all right, 10, I'm looking for 42, that's bigger than 10, so it better be in its right subtree if it's there. So then I'll go here, and I'll hit the 42 node, and oh man, is it there? And I found it. I can return, hey, yes, I found it, it was there. Maybe it's a key and it holds some other information, like a value as well, in which case maybe I'll give back the value, something like that. Or maybe it was enough to know that 42 was there, like this is a roster of students currently sitting in class for attendance or something. All right, let's now search for 7. It's not there, so let's figure out what's going to happen. We start at the root again, and, well, 7's bigger than 5, so I need to go right. So now I'm sitting at 10, and, well, 7's smaller than 10, so I need to go left, but there's nothing there. So once I go left, I see null, and then I notice that the thing that I was looking for was not in the tree. Okay, so I'll have to alert the user, maybe throw an exception or something. So that's the idea for searching a BST. And, well, we should talk about the complexity analysis of this, but first we should probably implement it. Okay, so let me do it for this tree here, and let's actually make this tree a bit better. 42, 3, 4, 7. So let's somehow turn this into a proper binary search tree. Maybe we can have 7. We'll insert 7 first. That can be the root. Let's see here. I'm going to copy all this. Call it bst examples.cpp. So we'll keep all this stuff. Let's make the tree look like this. Dun dun dun. Seven, maybe. Then 3, then 4, then 42. Okay, so now the left child of 7 needs to be 3, and then 42 is the right child. And then 42's left and right children are both null. It's now a leaf node. Then 3's left is null, but 3's right is 4. And then 4's left and right are both null pointer, because it's a leaf node, in theory. Yes, it was. All right, so now let's fix the parents. 7's the new root, so its parent is null. Oops. And then 3's parent is 7, and 4's parent is 3. That should be the new tree. And so now the root is sitting at 7, and these are all wrong now. Okay, so now I've got this tree, and let's write a search algorithm to search for a given key, okay? So let's be like cout search from the root for, I don't know, 42 perhaps. 42, and then also like something that's not there, like 5. All right, so search this function. Let's have it return, I don't know, bool, if it was there or not, perhaps. Bool, was it there? Search tree node star. Start searching from the root for a certain key. Okay, so now I'm going to implement this for you. So we're going to start the root, go left to right depending on what we're looking for. So if the key that I'm looking for, well, if it's smaller than the root's key, or I should probably do this in a different way, but no, we'll keep it like this. Why not? If the key that I'm looking for is smaller than the root's key, well, then, oh, sorry, the root's data, then that means, it's like I was searching for the 3 and I had a 5. That means I need to go left, okay? Okay, that's the idea. Otherwise, the key was greater, the thing that I'm looking for is greater than what I currently see at my root. Well, I need to go right, because it was bigger. It was bigger than what I had, so I know it's in the right subtree somewhere. And otherwise, we found it. Now we can, in this case, return true. Okay, so what does go left and what does go right mean? Well, it means, well, the new root of the tree that I'm looking at is the left subtree, okay? Now search the left subtree. It'll be the next root. And otherwise we go right, and we keep doing this as long as we haven't hit the bottom. So and that means that while the root of the current subtree we're searching for is not null. So either we're going to find this thing. No, I want to put that thing right there. Okay, never mind. It'll fix itself. There we go. So either we find it somewhere, or the root eventually becomes null because we've gone left or right a few too many times. We couldn't find the thing that we were looking for. In which case, if we ever get out of here, we we couldn't find the thing that we were looking for, in which case we'll return false. Okay, so I encourage you to take some time to look at this. Let's test it very quick before I eat my words and say that, yeah, it was totally correct. Let's search for 42 and let's search for 5 in this tree. This tree right here, that is. No, oops. Dun, dun, dun. So the first time it was like, yes, we found 42. And the second time it was, no, we didn't find 5. And the reason for that was, well, we started with our root set to 7. And then for 42, we went right because it was bigger. And then we eventually found it. But for 5, we're like, all right, it's smaller than 7, so I'm going to go this way. C3, oh, it's small, or it's bigger than 3, so I need to go this way. C4, well, it's bigger than 4, so I need to go this way. And eventually we hit null, which means it was not in the tree. Okay, so what is the time-space complexity of search? Well, space complexity is just the amount of, like the size of all the variables that we need. And so, how many variables do I need inside this function? Well, I need the parameters, a pointer that's like 8 bytes, an int, 4 bytes, and that's it. So I need a constant amount of space for search. I'm not storing, like, I'm not building up some kind of vector, I'm not building another tree. Constant. Not too bad. Just 2 values to store. Like, I don't know, 8 plus 4 bytes or so. Alright, let's talk about time complexity now. So the idea is, depending on what we're searching for, it's going to change. Like if we're searching for 7, that's like the best case. Let's talk about the worst case. The worst case complexity is, alright, I had to follow all of these edges. I had to follow so many edges and compare against the keys there. I had to follow as many edges as possible, and it still wasn't there, okay? So hopefully it makes sense why this is the worst case. Like, you gotta check 7, check 3, check 4, and then either go left or right, depending on what you search for, and be like, all right, it wasn't there, finally. So it's 3 comparisons, 3 go left, or 3 go lefts slash go rights. And what is that but a constant amount of work at each node times, dun dun dun, essentially the height of the tree. Okay. So, eventually, we're going to stop, return true or false. But we would have had to have visited the most possible nodes. And at each node that we visit, we do all this. We compare some stuff, at most 2 comparisons. And we might set some things, which is all constant work. So at each node that we visit, we do constant work. And we want to we visit O of the height of the tree nodes in the worst case. So it looks like search depends a whole lot on the height of the tree. So it's going to be O of h, where h is the height of the tree. And you can imagine a very imbalanced tree where this would suck, and a very balanced tree where this would be awesome. Okay? So I think that's where I want to leave us today. Next time we're going to talk about insertion and analyze that, of course. And then we'll get into some recursive things, lots and lots of recursion because you have lots and lots of subtrees. So that's going to take a while, and I will see you then.